Hello, I want to talk today about template matching and especially using cross-correlation in order to achieve this template matching. This is important when you want to figure out data association between images, or especially if you have a small image patch that you want to find or localize in another image. And that becomes very relevant as soon as you work with multiple images. So for example, you have two images like those two images of two mountains and you want to actually stitch them together in order to generate a panorama. In order to do that, you need to find locations in image number one and then determine where is this object being pictured located in image number two. So here this is done through some kind of distinct points found in the environment and then arrows telling which of them are actually corresponding. So if I take those arrows into account, I can actually stitch those images together here. So there's one example where you have some information in image number one, a local image patch, a distinct point, something that you want to localize in the other image. And then you're looking exactly for that local patch of image information in the other image. And if you do this multiple times, you get multiple of those data associations, saying which pixel in image number one corresponds to which pixel or which local area in image number two. That is also pretty relevant if you want to estimate 3D information from image data using multiple images. So for example, you have two images, it's kind of a stereo setup. So one image is taken from here, picturing this building here from the one side, and a second image of the building here looking to the portal directly from the front. And you know where those images have been taken, then you can use the images as well as the location information in order to perform a 3D reconstruction. In order to do that, you need to know which pixel in image number one corresponds to which pixel in image number two, or kind of observes the same point in the environment. So that you, for example, know that this part of the building over here is exactly this part of this building over here, so that you can perform this triangulation, so kind of intersecting those rays and then estimating the 3D location of that point. And what you need to do for that is, given you have kind of cut out, let's say, one point in image number one, you need to find where does this point sit in image number two, so that you can use this correspondence information to then perform, for example, triangulation and estimate the 3D location of that point over here. So making data association between parts of an image is a pretty frequently done task, especially if you want to look into 3D reconstruction. And data association is a challenging problem because there are so many different opportunities or possibilities that you have, and also so many opportunities for actually making mistakes and making wrong data associations. And wrong data associations are harmful for state estimation algorithms. So if you have outlier measurements, this can negatively impact your state estimation. Therefore, you want to invest quite some brain power in your data association scheme in order to get an as good as possible data association. You will not be able to kind of avoid data association mistakes all the time, but you want to look into your data association to see how can we do that as good as possible. And we need that data association, for example, for estimating 3D locations of points, estimating geometry, but also for other tasks. If you want to find kind of similar images, those kind of data associations play an important role, especially if you have multiple images taken from the same scene with a stereo camera or with a moving camera, and you want to identify what you have seen in image number one, to which pixel does this correspond in image number 2, 3, 4, 5, and so on. So the question is, how can we locate a point, or let's say a local patch, a local region that I have given from one image in another image? So you basically have a small query or template image, which is tiny, small region, and you want to locate that in the other image. So another task we may want to do this is, let's say you have an aerial vehicle and you're flying over the ground, you're taking pictures from the ground, and you take images at two different points in time where your airplane or your drone has actually flown a bit, and you take an image, so it's picturing the same scene, let's say a few seconds later, but from a different location, and you now want to make this data association. So these are two examples of these aerial images, also showing some kind of distinct points here. So some areas where some algorithm has said, okay, that's a point which kind of locally stands out. So this may be a good point to find that location in the other image. What you can also see here, I hope you can actually see that in the video, that the brightness and contrast between those images have slightly changed. So you also want to do this form of matching under similar conditions, but not exactly the same conditions. Obviously, you want to have pictured the same scene, and most of the time, the time spent between taking image number 1 and taking image number 2 is not too large, at least in this application over here. So it's maybe a few seconds or minutes, but not days, weeks, years, or decades, although there are clearly applications for doing this, but then maybe cross-correlation, the technique we are discussing today, may not be the best choice. But what we have even after in this short time spans is that we have different exposures of our camera. Sun may come out, your camera might trigger a different exposure. So there are reasons why the images, for example, change in brightness or also in contrast. And the key question is here, how do we know, or how can we know which parts of these images correspond to each other? So for example, if we look to one distinct point, let's say this point over here, where do I find this point in the other image? How can I figure out that this is actually this point? And that's what the approach template matching with cross-correlation is all about, and that's what we're going to discuss here. So cross-correlation is a technique that I can use in order to find image content in another image and also find its location. So I have a small image region, I say, okay, I want to find this, and I don't only want to know that it's in the other image, I also want to determine its location. So okay, it's exactly at pixel 100, 180, for example. And with all those approaches, we need to make assumptions. And the assumption basically tell us under which transformations we want to do this matching. And what cross-correlation takes into account is that there's only a translation, so a shift in the image. So both images are just shifted, not rotated, for example. So if you have an image number 1 and you rotate your camera, or you're flying a curve with your UAV, and you're kind of rotating your image, let's say by 45 degrees, and although those images overlap and you want to be able to find correspondences, this would be the wrong approach because it takes only into account translations over here. You can extend cross-correlation to also take rotational offsets into account, so you can extend that. It gets computationally more complex if you do that, but you can do that. But the basic cross-correlation, as we discuss it here, only takes into account translation. The second thing that the cross-correlation takes into account, it says it should be okay to have brightness changes and changes in the contrast in the image. So you want to find two images which differ only by a translation in their recording location and by contrast and brightness changes. And that, if you do that, then, or if you want to work under these constraints, cross-correlation is the standard technique to do that. Okay, so now let's go into a concrete example because cross-correlation is actually fairly easy to understand if you simply go through the individual steps and can actually explain that in a rather straightforward manner. So what we want to have, we have a template, a local region, the thing that I want to localize in my larger image. Typically you have a large image and a small template. Or the template is smaller and often much smaller than the original image. And the goal is to find this template in that large image. This template, again, is typically generated from your image number 1, from your initial image, for example. You cut out a part, we say, okay, that looks interesting, that's a distinct point, that's the location or the patch that I want to find in the other image. So that's your template. And then you take the second image, which is now the large image, and say, okay, where is that template or that local patch located in the other image? And what you want to, the information you want to get out, say, yep, here it is at that location. So if you look to this template, then we may be able to identify that this actually is this location over here. So this red box over here shows the overlapping area of the template with the image. In order to locate it, we want to have an offset where that location, where that patch is. So there should be a transformation between the local coordinate system of that template over here, which is here written as Q and P, and we have I and J over here in our original image. Then there's an offset indicated by U and V that describes where the 0, 0 location of my patch is. So let I say 0, 0 in the red, in the template, where is it matched to in the original image? That would be V and U. Okay, so the UV or VU vector is basically the shift vector that tells you the translation of the template and, let's say, a point in that template with respect to your original system. So you have a point P, which is expressed in this kind of red coordinate system, and by adding V and U to these coordinates, you can express where that point is in the larger image over here. So finding those offsets, V and U, are those two things which I'm interested in. So I want to find those offsets because once I have those offsets, then I know where that patch is located in the other image, and I can exploit this information for my further state estimation processes. Okay, so given we have an image which we call G1, this is kind of our large image, so the big one over here, that's G1. And we have the template G2, this is kind of my small patch that I want to find, my template. Then I'm interested in finding the offset U and V between G1 and G2. So I basically want to find the offsets in the X and Y direction or I, J direction for computing this offset vector over here. So we can express this as a geometric transformation. And if you remember geometric transformations, these are different ways how I can transform one image into the other. And you can do this, for example, with an affine transformation or similarity transform or rigid body transform or rotation or translation. And again, we are looking here only in translation. So we say one coordinate is the other coordinate minus this offset, this shift vector. So this here is our shift vector, which tells us how one is mapped into the other. That means we basically have two unknown parameters for our transformation, which is just this two-dimensional shift. So I'm just shifting this small template in the other image. I'm not rotating it or anything else. So this is kind of the geometric transformation that we're taking into account. There's also a radiometric transformation we want to take into account. And this is a transformation that accounts for the difference in brightness and in contrast. That's what we want to be invariant under. So we say the grayscale value in the template must be a constant offset plus a scale factor of the intensity value in my large image. So this is our translation-only constraint, and this A indicates the brightness because by adding a constant, I'm increasing the mean. By increasing the mean, I'm increasing the brightness of the image. And the factor in front of the intensity value changes the contrast of the image, increases or decreases the contrast. So it's something that we have seen in our initial operations when looking into histograms and transformations of images, that the change in brightness is a change in the mean value of our intensity values, and by multiplying this, I'm actually changing the variance and thus changing the contrast of my image. So again, this gives me two further parameters, A and B. So in the end, I have 4 parameters. I want to be invariant under those parameters, and I want to return those 2 parameters over here. But these are kind of the 3 parameters that I need to take into account in order to find a solution over here. And again, this is the result, and those parameters A and B I may not be explicitly interested in, but I want to be invariant under those 2 parameters. So my problem definition is basically finding this UV vector, this offset vector, under a transformation of the intensity values, which may look like this. And what I want to do is I actually want to find the location so that I'm maximizing the similarity between my template and my image. So if I compare that template with the overlapping area in the original image, then I want to maximize the similarity. May not be perfect, may not be absolutely perfect match. There may be some noise involved in this, but I want to maximize the similarity or minimize the difference between both. So the key question then is how to quantify actually similarity. How to say that 2 images are the same or are similar. Or the same would probably be easy, but because we can just see if the intensity values are identical. If so, we say yes, it's the same, otherwise it's not the same. But typically, again, we don't have the same characteristics, and especially that we have a radiometric transformation here. We want to have the similarity under this transformation, right? So if I'm just changing the intensity value, adding 1 to every intensity value, I still want to get the same similarity because I want to be invariant under this transformation. Okay, so what are typical ways for computing similarities between images, between intensity values? And there's a quite large set of ways you can do this, and just let's go through the most standard ones. So first, sum of squared differences, or SSD. So we take the intensity value in my template, subtract the intensity value in my original image. For every single pixel, I compute the difference between them, I square them, and I add all of them up. So basically the sum of the squared difference in intensity values. So if one intensity value is 100 and the other one is 200, then it's kind of 100 minus 200 squared. 100 squared equals 10,000 for one pixel. And then I'm actually summing up all those values. And that's it, what my sum of squared differences is. The smaller the sum of squared difference, the more similar the images are. Maybe I don't want to take the sum of squared into account, but the absolute differences. So I'm basically just subtracting those two, take the absolute value. So if the value is negative, I'm flipping it to the positive side, but I'm not squaring it. It's also called SAD. Or I'm taking into account the maximum difference, just saying what the maximum difference in intensity value in that local region where the images overlap. I'm just looking for the maximum difference of those intensity values. So there are 3 different ways how I can actually do that. These are standard ways for comparing images with each other or images with templates. But the problem with all those techniques is that they're actually not invariant under the radiometric transformation that I've introduced before. Mainly if I'm changing the brightness of, let's say, the image and not the template, this will actually lead to a different cost. So one image where I'm just kind of changing, making the image brighter, making one image brighter and comparing those images will actually give me a different measure of similarity. And that's something that I would like to avoid because I explicitly want to be invariant under this radiometric transformation that I defined before. So there's no, with all these 3 measures do not provide me an invariance against changes in the brightness or contrast of one of the images. And that's something that I would like to have. Therefore, we are in cross-correlation not taking into account those standard measures over here, but we go to take a different approach, and this is take the cross-correlation function into account. This is what it gives this approach its name. So what I want to do is want to again find the best offset by maximizing the cross-correlation coefficient over all possible location. So I'm basically saying I'm returning the best possible estimate those UV parameters that maximize this function over here. And this function, as you can see, has something to do with variances or standard deviations between the 2 images. And I want to go now a little bit more into the details on the next slide and explain what that normalized cross-correlation actually does and what the individual values here mean. And so you see the advantage of this technique is, of using this measure is that it's invariant under this radiometric transformation that I was describing before. Okay, so let's dive a little bit into the details and see what actually happens here. So the first part is the product of the variations of intensity values from the mean in the template image as well as in my original image. So I'm basically looking in kind of how far do the individual intensity values actually differ from its mean intensity value. So this means, for example, if I shift the mean in one of those images, but I'm only looking to the variations of the intensity values, this will actually give me the same result. All right? If I take one image and take my intensity values and I add, let's say, 10 to all intensity values, then the mean is higher by a factor of 10, by absolute value of 10. But if I'm just looking into the variations of intensity values from that mean in both images, then I'm actually invariant under that. Then I have down here the standard deviation of the intensity values in my image, in the original image, but not computed over the whole image, only taking those into account which are in the overlapping area of the template and my image. And therefore here the shift parameters matter, because I'm basically taking the size of the small image, overlaying it with a large image, where 0, 0 will be at that location, and then only computing the standard deviation of intensity values in that local area. So I'm taking the size of the template, overlaying it with my image at my position where I want to evaluate it, and then only compute the standard deviation in that local area. And the second one here is free of the parameter u and v, because this is just the standard deviation in my template, and no matter where it is located in the overall image, these are the same intensity values. Therefore, I only need to compute that once, and this parameter is independent of the actual location which I'm looking into, because it only depends on my template. Okay, so how do I compute those individual terms? So this one is the standard deviation of intensity values of my template G2. So how do I compute this? So the variance, this kind of the square root of this, so the standard deviation is the square root of the variance. I'm having the formula for the variance in here. So this is my normalizing term by the number of elements I'm taking into account, -1. So this is the number of pixels in G2. So uppercase M tells me how many pixels do I have in my template. What's the size of my template? Then I'm summing over all elements of all pixels in that template and summing over all rows and columns, so assuming that I can just have one sum going over them, not splitting it up into different sums, just to make it kind of the notation more convenient. So this basically means I'm iterating over all pixels in my template. And then I'm taking the actual intensity value of that template, and so this I subscript m and j subscript m means I'm basically mapping this index from 1 to m basically to the corresponding x and y values in that template. And what I'm subtracting from this is the mean intensity value over my template. So I'm computing the mean intensity value of my template. Then I'm subtracting that one from the actual intensity value. So this tells me here the deviations of the intensity values in the template from the mean. I'm squaring that. So I'm basically computing the squared difference for every single pixel, how far it is away from the mean, and then I sum them up and divide by the number of pixels -1. So computing the variance, and then I take the square root of that, and this gives me my value over here. Okay, so that was the first term. Now let's go to this second term down here. It's basically the same, except that I'm performing the operation now in my original image, in my image G1, and only in the area that overlaps with G2, because this is a comparison that I want to do. I'm overlapping two templates or two local regions. I will say how similar are those local regions. What happens outside is not interesting to me at that moment. So I'm again summing over all pixels in G2, so not G1, G2 it's important. It's not a mistake in here, G2. It's just the size of the template. And then I'm iterating over all rows and columns in that template and saying, okay, what is this value using the same index that I used before, and now subtracting from here the offset. So I'm basically saying, what I'm doing here, I'm taking the intensity values in one image and taking the offset appropriately into account. And then subtracting the mean intensity value of the image, but only located in this overlapping area of my template. And the rest is the same. The only difference is here, this computation depends on the index UV, because I'm basically only doing this computation in that small region. And then this part of the equation is the covariance between the intensity values that I have in my image G1 and my in the overlapping area, so in the area that overlaps with my template in G2. And so I do the computation here, one for the parts of the image that happens in G2, and the intensity values that happen in G1, taking always the mean of G1 and the mean of G2 into account, always in the temp area of the template. And if I compute this normalized cross-correlation value, that means large values will tell me, yes, the two images are identical under this measure. being invariant with respect to translation and shift. And if this is a low value, then this is not the case. Okay, so I now defined what transformation I'm allowing, and I told you how I measure similarity now. Now the question is, how do I actually find the best position? So how do I determine where that local small template sits in my large image? And what I need to do for this, I simply need to compute this measure, this similarity, for all possible offsets. So I say, okay, what about offset 0, 0? That means I'm sitting over here. What about the offset 1, 0, or 0, 1, moving 1 here, or 0, 2, or 0, 3, or 0, 4, and so on and so forth. And then through the individual rows and columns. And I'm basically taking this template and I'm basically sliding it over my image and evaluating that image at all locations. So as a result of this, for every possible shift, so which is a U and V coordinate over here, I get one of those normalized cross-correlation values. And these I can represent here at kind of this hilly landscape, not very smooth, of cross-correlation values. And then I said, okay, I want to take the one which shows the best performance. So where the row value, the normalized cross-correlation value, is maximized. And this is here at that location where kind of we have this red peak over here, and this exactly corresponds in this example here to the true location where that point actually is. So it's basically an exhaustive search that I'm computing, trying all possible intensity values and see if they would actually fit. What you can see in here is that there's also one way how I can increase this approach to taking into account rotations, for example. So the naive approach now to take into account rotations, I'm not just sliding this template over the original image, I may also rotate that template and try all possible rotations, sliding them over the image. And then, of course, for every possible rotation, I need to slide over that image. So it gets computationally much more demanding the more possible parameters for that geometric transformation I'm going to add to that. And therefore, we are sticking here just to translations, so shifts in the delta x, delta y pixel coordinate. So in terms of the complexity of this approach, so we're basically doing an exhaustive search or full search in the space of 2D translation parameters. So I'm basically trying out every possible location. Of course, I need to not do all possible locations where the template and the images actually do overlap. And as I said, we could also look for rotations or other parameters, but that increases the complexity, and the complexity actually increases with the dimensionality of that search space. So the number of parameters I need to test for the shift in x times the shift in y times the number of rotations times the number of whatever shear parameters or scale parameters I want to take into account. This all adds up and I need to multiply those values. So the complexity grows very, very quickly. And therefore, I want to reduce the number of dimensions or keep the number of dimensions that I need to take into account in order to have not a dramatically increasing complexity, being unable to compute the results later on. A few notes about how we do that in practice. One's to be more robust and the other one to also be relatively fast doing this. We don't using the original image immediately. So what we are typically doing is we're using downscaled versions of the image to first localize the patch roughly and then perform a fine-based analysis. And this we can do using an image pyramid. Remember, image pyramid is something that we discussed in the chapter of geometric transformations. These are differently scaled versions of the image. For example, halving the size of the image from one level of the pyramid to the next level of the pyramid. And one way I could do this, I could simply, if I use the original image, I would need to slide over the whole image on the lowest level. That would be the naive exhaustive search approach that we have described before. What I can do as an alternative, I'm first looking for the template only on the highest level of the pyramid. And so in this case, I can basically actually nail it down where it actually is located. And then I say, okay, now let's say the resolution of this area here is just whatever, 16ths of the resolution of the area down here. So I have a higher uncertainty where it actually is located just based on the discretization that I have. But then I can say, okay, I can now go one level down and start from this point and only need to look in this local area that overlaps with the original template and can kind of pinpoint where the template is at that at this kind of lower resolution. Then I can go a step down to the highest resolution level and can actually find my template. So this is a way how I can iteratively go from one level to the next level until I am at the most high resolution level and find my template over here. I could also use the pyramid if I want to look over scales. So if I don't know if my template has been scaled, then I can of course use a different approach, and then I simply need to make sure that I don't actually scale the template when I go through the different levels of the pyramid. But these are kind of two different approaches, but that I can both address using the pyramid over here. Okay, let's look into a small example to get a slightly better understanding of what actually happens here. So consider these are 4 examples, A, B, C, D, of images that I want to have, and I have templates which actually look like this. So how well does lowercase a matches uppercase a? So this is one example. So how well does cross-correlation allow us to pinpoint this area in this image? How good is that? So wherever I slide lowercase a and uppercase a, it will always be a perfect match. Right? So there's no area which stands out, which allows us to localize this point. So the normalized cross-correlation coefficient will actually be very high. The normalized cross-correlation will be high, will return a high value. But none of the values actually stands out. And if none of the values stands out, there's no way that I can say whatever offset 2,2 is better than offset 10,10. So as a result of this, I will basically find no match because the similarity value is the same everywhere. Okay, let's look at the second example. How well does lowercase b fits into uppercase b? And it turns out that they are locally distinct areas, so I can slide it, and we will get different values. So we won't suffer from the problem that we have here in our first example. However, there's no unique solution because this small template basically fits over all intersections of these horizontal and vertical lines. Maybe not this one over here because maybe the circle would overlap, so it would get a slightly slower value. But basically for all crosses or all crosses where there's no other pattern or texture in the local surrounding, we will actually get a high value. So we will have basically a multimodal solution or an ambiguous solution. We say it's either here or here or here or here or here or here or here, and so on and so forth. So we are not coming up with a unique solution, but we have several matches. So we can return several possibilities for those overlapping areas. So then I have C in this area C over here. What you can see is wherever I slide that, I will actually get no matching result. So there should be no result where I get a value that is high, let's say close to 1 or 80%, something like this. So I should find no match here, at least. There will be one value which may stand out, but this value will be really small. And as a result of this, this will not be a match that I'm taking into account. At least if I take for my values of row only positive values, if I would go to -1, then I probably would find a match over here. When black turns into white and white turns into black, then I actually would find a match over here. But assuming I'm not doing this, I'm only considering values that say higher than 0.8 or something like this. And then last but not least, matching lowercase d to uppercase d. If you slide this template over this image, there's exactly one location where I have a good match, which is exactly this overlapping area over here. So if I match D with D, I will get exactly one match where row takes a large value close to 1. In this example, I would find a match over here. Okay, so basic cross-correlation. What are the kind of key properties? How we do this? So it's basically a search for a template image in another potentially large image. And it's fairly easy to compute. The only thing I need to be able to do is computing basically variances in means of intensity values. And I need to have an approach which basically slides a template over an image. So it's relatively fast and easy to compute, at least fast If I only have translation parameters, if I take more translation parameters account, this can get computationally costly. Cross-correlation in its basic form allows only for variations in brightness and contrast with respect to the radiometric transformation and the translation for the geometric transformation. There are extensions of the basic cross-correlation, therefore I call it here basic cross-correlation, which can do more, but this is kind of the standard approach that we are doing. And through this, using this normalized cross-correlation function as our similarity function, we actually have a transformation which is invariant to brightness and contrast changes, and thus with this measure I can easily just compare the geometric translation parameters or transformation parameters, which are the translation, in order to, with an exhaustive search, find the best parameter set. So this was basic standard cross-correlation, performing this matching up to pixel level accuracy. But we may want to have more. We want to go down to sub-pixel matching. And so the question is, can we actually do sub-pixel estimation of cross-correlation? So let's say we had this example that the airplane is flying, taking 2 images. There's no guarantee that actually the world is shifted by exactly 1 pixel or exactly 2 pixel. Maybe it's 1.5 pixel or 1.8 pixel or 2.9 pixels. And so we may want to get better than just pixel precision for our matching. And the question is, can we do sub-pixel estimation for the cross-correlation approach? And that's something which I found surprising when I saw that for the first time as a student, that you can actually do this sub-pixel matching. But I hope I can convince you that it's actually a good idea to do and that it's actually not too complicated. And we have all the tools at hand that you have learned in this lecture, in the last 2 lectures over here, looking into geometric transformations as well as local operators and convolutions in order to exploit those properties and in order to perform sub-pixel estimation using cross-correlation. Okay, so let's dive into that and see how that looks like. So what we want to avoid is this kind of integer valued possible shifts, so saying I can only be shifted by 1 pixel or 2 or 3 or 4. I want to be able to say this template has been shifted by 7.3 pixels, for example. And we can obtain that by not taking into account shifts that only happen at pixel level, but going into sub-pixel estimation. And for that, we need to take into account that the templates and the images that we have are actually coming from a continuous function, from a continuous light intensity function, which we just sampled at some distinct locations. So what we have in our image is basically different intensity values like this. And as a result of this, having this discretized intensity values, we will have also discretized normalized cross-correlation function values, right? So these values over here that we compute are a result of the fact that we have the pixel discretization in our image, and this actually stems from a continuous function. So if the actual intensity values are a continuous function, then also this normalized cross-correlation should be a continuous function. So let's draw in a continuous function over here. So a function which actually fits to my intensity values. And then I have, for example, 2 values over here which have similarly high value. Then the maximum value is not this point or this point, it actually sits between. So this value over here will actually be the optimal or a better, it's called optimal matching value, assuming here a continuous function which doesn't do some whatever super crazy movements over here. So it's optimal solution under some assumption that there sits a continuous function between this discretized measurements at discretized locations that I have measuring my pixel intensities, and the result of this, my function rho. So the question is, how can we do better? How can we actually obtain the actual maximum? And we try to do this by using the nearby values, estimating how that red function actually looks like, and then trying to maximize that red continuous function. Okay, so what we do is we basically fit a smooth function, or in 2D a surface, through our function rho, our similarity function, and start with the position that we have found from our standard cross-correlation, saying, okay, here's the maximum, the best possible match. Let's look in this local surrounding by taking neighboring values into account, estimating how that smooth function potentially looks like, and then estimating this kind of a local maximum. So we still use our basic cross-correlation function as a starting point for determining where we want to go deeper. Okay, and what we're doing is we are, again, this is an assumption, but we are fitting a quadratic function around our measurement value. So we're saying this intensity, or this normalized cross-correlation function is a quadratic function where we only have kind of sampled locations from in this local neighborhood, so a locally quadratic function. And the good thing is through the standard cross-correlation, we have estimated already kind of the local, where it is on a globally up to a local area, and now we just need to do the refinement in that local area. And if you have a quadratic function, you say, okay, x is our function, our offset, and x star is this unknown thing, this unknown maximum that I want to determine. And so this function, so we want to actually find x star, that's what we want to have. Let's assume we know it for the moment, and this is kind of our unknown maximum value. And this is our quadratic form that we have here as a 2D function. So this x and x star are 2D values, and A is then a 2x2 matrix, and this is here a 1D additive value that comes with it. Okay, so let's start with this. And what do we need to do in order to compute the maximum of that function? So it's a quadratic function, so it's basically a parabola in 2D. And we know that if you want to find the maximum or the minimum, depending if the parabola opens to the top or to the bottom, we need to look into derivatives, right? Because at the minimum or maximum, we have the first derivative being 0. So what we need to do is we need to take that function, this quadratic form, and need to compute the first derivative. So this is our first derivative of my function, and this is by using the standard of computing a derivative of this quadratic form. This will be 2a times x minus x star, and we know that at the maximum this first derivative must be 0. Well, the only thing we did is we said, okay, we assume the function looks like this. Again, this is an assumption, but we said we assume the function looks like this. Let's compute the first derivative, and we know that the first derivative must be 0 for if we put in the maximum value over here. And this is what we will use in order to compute this maximum value. Okay, this is our first derivative, and if I compute the second derivative of that, so my Hessian, then it actually turns out that the Hessian must be 2a. So if you would compute the next derivative with respect to x of this term, it's only the constant term here that would survive. So the Hessian will be 2 times this matrix A that we don't know yet, but in a second we'll actually figure out how that looks like. So this is the Hessian of my normalized cross-correlation function rho. So if we just replace the 2a by my Hessian, then this function turns into the gradient, the first derivative of my function rho equals to the Hessian times x minus x star. So what I can do is I can compute the inverse of the Hessian from the left-hand side. So h rho to minus 1 moves over here. This becomes the identity. So I have this term which remains, h inverse times the gradient equals x minus x star. And x star is the thing that I want to determine. And if I said, okay, I want to determine x star, that's easy. I'm just moving x star to the other side and those elements on the right-hand side. So x star equals x minus the Hessian evaluated at the location x inverse and the gradient evaluated at that location x. Okay? So just kind of, this is just a result of setting the first derivative to 0 and doing some replacement. Why did I put the Hessian in here and not leaving 2a in here? We'll come to that very soon, because for that function we can actually compute the Hessian and we can see in a second how that actually looks like. So if I have an image, and I can see this cross-correlation function basically as an image, right? So we evaluated it at every location, so we basically have a 2D grid with some discretized value. You can see this is very similar to an image, where we basically want to select the highest value out. So if there's an image, then we can say, okay, let's go back and look to the individual values. So my x is my two-dimensional shift vector. This function here is actually the gradient, so the first derivative with respect to I and the first derivative with respect to j, so the different parameters over here, evaluated at the location x of that two-dimensional NCC function, which I can interpret as an image by now. And this term here is the Hessian, so the matrix consisting of the partial second derivatives arranged here in this matrix form, computed at the location x. Also of this NCC function, which I can interpret as an image. And now, if you have attended the lectures on convolutions and how to compute gradients of images, you know that for an image we can very easily compute a gradient or the partial derivatives, which we need to set up the gradient and the Hessian matrix. And this is something that we can do, for example, with our Sobel operator, as well as with our other operators for the second derivatives that we have defined based on the convolutions. So we can, through our convolutions, convolve an image and get its gradient or its second derivatives. And we can do exactly the same thing here, although the NCC is not an actually intensity value, but the fact that it was an intensity value is something we haven't exploited when computing the first derivatives of images. Just as basically it's a discretized 2D to 1D function, which we have only at discretized locations, and that's what the NCC perfectly is. So what we basically do, we are using the Sobel operator and the operators for the second derivatives, but not executing it on the actual image, but computing it on the NCC result. So based on this function that we have, where we run our exhaustive search for, but doing this only in the local neighborhood where the function where I actually found the maximum value. Okay, so these are all the quantities that I actually need to compute. So my x star I can compute with x. This is kind of the result that I had from my basic cross correlation. So this is the outcome, the result of my standard cross correlation approach. And then I need to compute the first and second derivatives. And if you go back to the chapter on the local operators, this was have been my Sobel operators, and I have the operators for the second derivatives. And I only need to convolve them with my function rho, which I already computed. And then I can start from my current estimate that I have, and then take kind of the small variation into account to estimate where the maximum value for the cross correlation is. And this gives me an update. So this term gives me an update on the initial guess that I have from my basic cross correlation, and tells me in one step where the maximum value is. So it's basically a local shift in x and y. You're going to say, okay, move a little bit in this direction, and then you're better off. And this allows us to get a more precise localization, a sub-pixel estimation of the shift. And it turns out that you can actually get a result up to a tenth of a pixel in terms of precision. So although you have only individual intensity values at every pixel, you can increase the precision by roughly a factor of 10 or up to a factor of 10 in order to make a sub-pixel estimation of that translation. I found that quite surprising when I saw that for the first time, but it simply results from the fact that it's a discretized function. We make this assumption of having a locally quadratic form and then estimating this maximally quadratic form. And the cross correlation actually provides us with an optimal solution if we only take translations into account and only the radiometric transformations, or having this measure which is invariant under the brightness and contrast changes of our image. There are also some assumptions which are involved in here, so that we have equal and uncorrelated noise between those images. Of course, if we get rid of those assumptions, then things will get more tricky. And also what we should take into account, something that cross-correlation can't deal with, are things like occlusions. So if you have a bird flying underneath your airplane while you're taking the image and the bird overlaps that local region, you actually will not be able to find the matching position, at least if the bird is close enough to the airplane to cover a substantial part of your local patch. And again, just said that there are optimizations for certain situations, extensions of cross correlations, how you actually can do better or adapt to certain local setups that you may have. Also, if you change or violate the assumptions that we had before, especially with respect that it's only a shift, that's something that's not always realistic. If you violate those assumptions, still cross correlation works not too bad if you have, let's say, a rotation of 5 degrees, for example. If you're going to something larger than 20 degrees or scale differences larger than 30 degrees, then you're violating your model assumptions substantially and typically don't get good results out of that anymore. If you stay substantially below those values, you can still apply cross correlation and get reasonable results unless your environment is very ambiguous, for example. Then the question is how well that actually would work, or if the violation of those assumptions doesn't create artifacts or noise which is larger than than the variations you actually have in your original image. So be careful if you are above those values that are indicated over here. Okay, with this, I'm coming to the end in template matching. Cross correlation is a standard way to perform this template matching. There are, again, for certain setups, better ways for doing this. So for example, if you have your stereo camera and you know that there's a different orientational change of your camera, maybe that's not the best choice to use cross correlation. You may want to explicitly take into account those rotational informations. But as long as you have only translations, that's a standard way to do. It's easy to implement, fairly fast if you only work in 2D. And with this subpixel estimation, which can also be done very efficiently, you actually get you get a quite accurate matching of up to a tenth of a pixel. With this, I'm coming to the end, and I hope you learned something on how to find data associations between two images by comparing patches of images, or taking a patch in one image and look where it is in image number 2, which is a basic step, for example, in stereo reconstruction if you want to make the data associations between your the right and the left image in your stereo camera. You can do this either with this template matching procedure, or other ways for doing this is using features, something that we will also explore here. If you find distinct points and have a local description of these distinct points, it may be faster for you to try to match those points with others and compute kind of descriptors or feature descriptors of these points. The attractive thing in here is we can actually basically take a local region. We don't need to consider what kind of local structure is in there and trying to find possible matches of that template in the other image, which is kind of one of the basic techniques to do that. And I hope that was a good introduction into those basics. So thank you very much for your attention.